Nice out here.
Oh.
And why wouldn't we do this in the studio?
I'm having a hard time seeing you.
Why
Steve.
am I wearing gloves? Like you're wearing warm gloves and I'm wearing
Yeah.
these latex or whatever gloves. That spill on I-25, the sulfuric acid spill, was a perfect opportunity for teachers around the Denver metro area to talk to kids about sulfuric acid, especially those chemistry teachers. So I brought you some sulfuric acid to be able to show you some of the properties. Now, concentrated sulfuric acid is 18 molar, and
what does that mean?
It indicates the strength.
Okay.
And by itself, chemists, believe it or not, consider it a pretty weak acid. It's only when it gets around water that it gets to be pretty dangerous, and that's what the danger was on I-25, is it being around any water. So watch this. I'll show you a kind of a classic science demonstration. This is powdered sugar. So I have powdered sugar in the beaker, and so that's all I'm using here is powdered sugar. But powdered sugar has a water molecule associated with it, 11 of them, in fact. So here's our sulfuric acid. So you got your gloves or your glasses on and so forth. So I'm going to pour the sulfuric acid inside like this, and now mix it around, and you can start to see the reaction almost instantaneously. And then all of a sudden you'll see it turn very black very fast, and then it'll be like a s'more. So here, kind of watch the reaction there. So you see how it starts to turn this way?
Oh, and it stinks.
Yeah, oh, there is that. So there's our fumes coming off, and you'll actually see it start to decompose. And so as it starts to come up and decompose, take a look at this.
Holy cow!
Is that just amazing?
Wow.
So you start to see that moisture coming off. Kind of like when you're at 4th of July, you know, and you've got one of those things. Honestly, you're done having kids, aren't you? So, so the fumes are pretty, yeah,
Steve,
exactly.
appreciate
So
that.
look at what it did. It dehydrated it. So literally all we have left is carbon. Isn't that an amazing
Wow.
thing?
So
So we
what's
worry
the-
about that.
What was the danger with this in cars then?
Well, if it gets on the car, it's very, very corrosive once it comes in contact with water. So they use it. I mean, it's the most
I see.
used industrial chemical. There's more sulfuric acid made than any other industrial chemical. The other thing that they're concerned about is what it mixes with. And so it wouldn't have mixed with this particular material here, but the first responders are always worried about what another chemical might touch. So this, for example, is sugar, so regular table sugar, and a strong oxidizer. They're kind of like the heads of a match, you know, the white part of the match. And so I have that there. It's called potassium chloride. Here's the power of just a single drop of sulfuric acid. So I'm just going to use one little drop of sulfuric acid. Watch this. As it gets close here, here's the one drop of sulfuric acid.
Whoa,
you start to see it take off. Is that just amazing?
One drop.
One drop, and so that would trigger another reaction. And so that's not because of the sulfuric acid, other than that sulfuric acid was just the catalyst for that.
Right.
Why didn't you let me do that at your wedding? I think both of those demos would have been fabulous for the guests.
I don't think my wedding planner would have really.
I'm telling
gone
you,
for that,
see,
Steve.
but you could have just touched it and just like that. Yeah. This is sulfuric acid. It's something that we have a tremendous amount of respect for, but what a great opportunity. Horrible that the accident happened, but a great opportunity for us as teachers to be able to share some real world things with students.
Well, thank you so much, Steve. This has been really interesting this morning. Yeah.
It smells like s'mores, doesn't it?
It really does not smell great out here.
In our safety rules, we have a section where we ask students to wear aprons or lab coats in the lab, and we talk about how that's important to protect their clothing. Once again, I think it's a nice idea to illustrate what can happen when chemicals do spill on your clothing. The reality is that most anything that we work with in the laboratory and you spill it on a student's clothing isn't really going to do anything to the clothing. We don't really work with highly concentrated acids very often, especially in a first-year chemistry course, but they don't need to know that, and they really don't know the difference between 18 molar sulfuric acid and 10th molar sulfuric acid or 100th molar sulfuric acid. It all pretty much means the same to them, and in fact, when you say 100th, it sounds more impressive than 18 to some kids. Oh, yeah, 100th, that's pretty scientific, especially if you say 0.01 molar. And it's like, oh, that's a scientific thing. That could be dangerous. So it's, you know, we want to illustrate again, okay, what's the importance of wearing an apron, the rubberized apron of some sort to protect your clothing. And I used to do this as two separate demonstrations, and at some point in time, it sort of evolved into one thing together. I think the evolution occurred when I discovered that they sold these styrofoam wig heads and that they were easy to pick up without too much trouble. And so I like to illustrate what happens or what can happen when you spill a chemical on your clothing, and also that some chemicals react with one material but not necessarily with another material. So I've got some 18 molar sulfuric acid here, and I've drawn a little bit up into a transfer pipette. And I'm going to drop a little bit on this nylon, and we'll see what happens to it. Well, this is one of the things that I always think is so cool, because I never know what color it's going to turn, and I have no answer for why it does. Some of the nylons, you know, the dark black ones will go red. This one is turning kind of purplish blue. I've never seen that before. I'll have to go back and look and see what color these happen to have been. And I'm just guessing that it has something to do with the dyes they use. But you can see what's happening here with this is pretty amazing and quite effective. A few drops of this, and the drops eat through almost instantaneously, which is, by the way, what your students expect to happen. Because that's what they've seen in the cartoons, and that's what they've seen in some of the movies. You know, where the guy spills a little bit of concentrated acid on his hand, and 3 seconds later, you can see the floor through their hand. You know, because, and there's no sense in necessarily going beyond that with them. I mean, then they're going to get to the, you know, if they do spill something on their hands, they're going to go wash it off right away if they think it's going to eat a hole in their hand. If you tell them, you know, well, you could spill this on your hand and you really don't have to get to the station for 30, 40 seconds, wouldn't be a problem. A couple of minutes probably wouldn't make all that much difference as long as you get over there and wash it off fairly fast. But this is kind of neat, and I like this. But you'll notice that while the acid has done a pretty decent job of attacking the nylon, it hasn't done anything to the styrofoam. It's remained pretty much undisturbed. The acid breaks down the linkages in the nylon. Nylon's got something similar to a peptide bond in it. It's a nitrogen-carbon bond. And I don't know this for a fact, but I believe that the sulfuric acid attacks that bond, and that's what breaks it apart and what makes it dissolve. The color change, I think, has to do with the dyes they're using in it. And it just happens to be some sort of acid-base indicator. I've never tried this. It'd be kind of cool to put some base on here sometime and see if it changed another color. But a different chemical will have an entirely different effect. If I take, and I'm going to spin this head around briefly here, and use acetone, nail polish remover, for, well, used to be an all nail polish remover. Now there are some that don't contain acetone. I believe you can buy acetone-free nail polish remover. But if you pour this on the nylon, and what I'll do is I'll pull this up a little bit so it's off to the side. Just dump some there. Nicely done. Got it everywhere. But you can see the nylon is essentially unaffected. It's not changing, doesn't do anything at all. On the other hand, when the acetone hits the styrofoam, we get an entirely different effect. Help me! And again, this is what your kids expect to happen when you pour acid on it, on themselves. I'm dissolving! This isn't a half bad thing to do at Halloween too, or right after they've done The Wizard of Oz on TV for the umpteenth time. I'm dissolving. Now, you probably know that styrofoam doesn't actually dissolve in this process. All this does, the acetone weakens the linkages in the polystyrene and it lets the gas out. And so when you get done with this, you'll find that you've got this gooey crud that's there, which, by the way, you really want gloves for this thing because this is not just polystyrene and gooed up nylon. There's also some sulfuric acid in here at 18 molar. You're not sticking your fingers down in this without that. Well, you can do it, but you can probably only do it once. Well, I don't know. Let's see. If I use 2 fingers, yeah, I could probably do 5 classes. Be in a day. So, again, a nice illustration of why I want to wear my lab apron, to protect not only my clothing, but also my body, which is underneath that clothing.
what I have is some barium hydroxide. Okay, and I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
What's with the hand stuff?
What hand stuff?
The hand sanitizer gel.
Oh, it just lives on my desk.
Oh.
I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second.
Sweet.
So, I'm going to mix these two things together and carefully... in fact, I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to put it in coffee. Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best one you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. And that is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So
Freezes at 10.
this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to melt. In fact, there's actually ice crystals forming on the side of there.
Can I touch the side? It's
cool.
so cool.
Yeah. No.
What's being generated over there in the acid can, oh my word. We're going to show you something with aluminium today. And the thing is, we've got here Coke cans and Pepsi cans as well, so that it's fair. But when Neil gave them to me, I had a look inside, and you can see there, this one has quite clearly rusted. So these Coke cans are made of aluminium, whereas the Pepsi ones are steel. That's why we can only use the Coke cans to do this next experiment. So what we're going to do with these is to show a property of aluminium and how it reacts with both acid and with base. And that means it's a substance that's amphoteric. What we're going to do is we've got a solution of sodium hydroxide, that's our base, and we've got also hydrochloric acid, and then Neil's going to put the acid in and I'll put the base in at the same time, and we're going to see what happens to the aluminium cans. Yep. Go. Oh yeah, straight away you can see the bubbling there with the base. Clearly you've got a very vigorous reaction in both cases. So what's being generated here is sodium aluminate. And what's being generated over there in the acid can, oh my word, is aluminium chloride and water. We expected reaction with both, yeah, I hadn't anticipated to be quite so vigorous. I hadn't expected it to be quite so, wow. That is brilliant. So this is obviously a very vigorous, hot reaction. You've got a lot of fumes being given off, which is a good job why we did it in the fume cupboard. You can see all that smoke being drawn up into the extraction fan. I honestly thought the acid would have done more damage. Because when you think of acid, you always associate acids as being the evil guy of the chemical world. I think those Pepsi cans have gotten off very lightly. They may have had their tops cut off, but they've met a fate far better than the Coke cans here. Good old Pepsi for making them steel. Neil, can you clean that up for us? What's left is just the plastic around the outside of the can. All the metal's been converted to sodium aluminate. And that one's still going. The acid is still eating away at that can. And again, it's just leaving behind the plastic coating. It was a really exothermic reaction. And I didn't think I would actually see a can bubbling away like that. That is just incredible, isn't it? It looks pretty disgusting.